Hi everybody, this is Jim Corkins, and we are now starting 5.0 Introduction to Magnetic Fields. So please go ahead and start reading chapters 21 and 22 in Coletta. If you have OpenStax, and you're in Physics 112, this will be chapters 22 and 23, as well as in Physics 131, it would be chapters 11, 12, and 13. This is related to Homework 6, Magnetism, if you're in Physics 112, and Homework 8, Magnetism, if you're in Physics 131. Okay. So in this entire topic of magnetism, we're going to go through what causes magnetism, what are the sources of magnetism. Later on, we're going to work on how current is related to magnetic fields. What are magnetic dipoles? We're going to be applying Ampere's law as well as a Biot-Savart law. And finally, we're going to get into how magnetic fields and interacting magnetic fields cause forces. Okay? So chances are you have had some really interesting experiences related to magnetic fields and magnetism in general, right? So we've all played around with magnets, and your refrigerator door has little magnets on it, probably holding up pieces of paper. We use magnets in nearly every piece of technology, especially speakers, hard drives, as well as the creation of energy, with generators and electric cars. So the Earth also, you've probably held a compass in your hand and noticed that it points north. Okay, so that's the Earth right there. And so you've probably done all of these things. And a compass, by the way, is just a little magnet floating on a balance beam. So you've probably had a lot of experiences with magnetism. So what we're going to get into next is talking about what causes magnetic fields. All right? So what causes a magnet? What is a magnet made of? Okay? Well, essentially what it is electrons that are orbiting about an atom, but also these electrons are spinning. So basically, you have these little electrons that are orbiting an atom, but also these electrons are also spinning, all right? And what you're going to learn later is if it's got a counterclockwise spin, that is called spin up. And if it's got a clockwise spin, that is going to be called spin down, right? So what these are called are called quantized. The motion of these electrons are quantized, right? And so if you have paired electrons in an atom, one is spin up, one is spin down, then that net spin is going to be zero, right? A counterclockwise spin up, a clockwise spin is down. So when you add those two things up, one's positive, one's negative, it's going to have a net spin of zero, right? And so what you need is you need atoms that have a lot of unpaired electrons, okay? Where instead of having two electrons bound together, you have just one electron, right? So an abundance of these unpaired electrons is what causes these magnetic fields, right? So iron, cobalt, and nickel have a lot of unpaired electrons, so they can't cancel out. So that means they have a net spin and a net orbital motion, and so there will be a magnetic field produced, or at least a possibility of a magnetic field to be able to be produced. All right. So basically, it's the overall motions of the electrons that give rise to atoms, give rise to magnetic fields. And not only that, it's the unpaired. You need unpaired electrons to do this. So it's the spin, it's the orbital motion of unpaired electrons that cause these. So if you notice, like a lot of material is not magnetic, and it's actually only a select types of materials that are magnetic. Okay. There are two things going on. So if you notice that your refrigerator door by itself is not magnetic, right? If you take another piece of iron and put it up against your refrigerator door, it'll just fall to the ground. So right now, the iron in your refrigerator is actually a ferromagnetic material, meaning it's not currently magnetic, but if it was put in a certain condition, and how you would do that is you would heat up the iron, and it starts to boil, and so those spinning electrons can now be free to move, and then as it's hot, you put it in a really strong magnetic field, and then you rapidly quench it and cool it down, and what it does is it locks those little electrons into place, and now it is a permanent magnet. And eventually, what will happen as systems degrade and things like that, it can become ferromagnetic again. So iron, cobalt, nickel are probably naturally just ferromagnetic, but then you could put them through a process to make them a permanent magnet. Okay? So again, the main causes of magnetism are unpaired electrons that are spinning, basically spinning and orbiting a metal. Okay? And again, there's that kind of system where they're either a permanent magnet or they're ferromagnetic, and that means they're a temporary magnet where they could become magnetic under the right conditions. Okay, so it's really interesting too. Even though iron by itself, the iron in a refrigerator is not naturally, it's not magnetic at the moment, right? But if you put a magnet close to it, then it could become magnetic. And we'll talk about that. And we'll talk about those conditions of how that happens too. So let's take a look at what is happening inside iron, and look at the difference between just iron that is ferromagnetic, meaning it's not magnetic at the moment, and what iron looks like when it is magnetic. Okay? So normally you have iron, and I'm going to mark up the document here. You have iron that is ferromagnetic, and this is a permanent magnet. I don't know why that keeps happening. Click that off. So this is iron, and it's the same iron as this. So there's nothing special about this iron, which is it's not magnetic at the moment, and another hunk of iron where it is magnetic, right? They're the same exact chemical makeup, right? But if you'll notice that these guys, so first of all, the direction that it points is the dipole, right? It's the unpaired electron. And it's going to be rotating counterclockwise, so CCW, okay? And at the top of this is the north. It's a little magnet in and of itself, and that is going to be south. And so the bottom is going to be south, right? So this guy is rotating counterclockwise, and what you'll notice is that all of these guys who are rotating counterclockwise are all rotating counterclockwise, pointed in the same direction, right? So all of these little guys are rotating counterclockwise, and they're all pointed in the same direction. Well, what you have is then it looks like it's a density issue, right? So this is like the density, and I should actually use the term sigma. No, it's a volume density, so rho, and it's the density of magnetic dipoles per volume, right? And that is what is the value of that magnetic field produced by this, right? So it's a density of the magnetic dipoles pointed in the same direction. Or you could also say is the net, net dipole moment per volume. And this is a volume, okay? So essentially, if you have all of these guys are all rotating and spinning in the same direction, okay, and then what happens is the top of that, where all these guys are pointed in the same direction, if that top of that spin is north, then that is going to be north. And if the bottom of the spin is south, so this is south down here and that's north up there, then that means this is going to be the south direction, right? And if you'll notice too that these are called dipoles, dipoles meaning two poles, north and a south. You always have to have a north and a south. You can't just have a north. If there's a north, there's got to be a south, essentially. Well, in iron, that is not a magnetic, a non-magnetic piece of iron, or what I like to call, what is also called a ferromagnetic, means it has a potential to be a magnet. Well, all these guys, these are the same guys as over here, but they're just kind of pointed all over the place. So this guy's pointed up and to the right. Is pointing down and to the left. So they're kind of canceling out. Well, this guy is pointed, these guys are canceling out. Okay, and these guys are canceling out here. Whoops, that should be south, and this should be north. And if you notice, you have a lot of things canceling each other out here, okay? And that may be getting canceled out by what is happening over here. So they don't have to be right next to each other either. So when you add up all of these guys, their net, the net dipole moment, is 0, right? And so, since these guys are just kind of all over the place, this object right here, this piece of iron, is not magnetic at the moment. It can become magnetic under the right conditions, right? If you wanted to make this into this, if you want to make the ferromagnetic iron into a permanent magnetic iron, what you got to do is increase the temperature. So these guys are stuck spinning. This guy will be stuck spinning in this way. And it's kind of locked in this other guy, this other piece. So what you have to do is break up these bonds in between, and how you do that is you add temperature. So you heat it up, and then what you do is you put it in a magnetic field, a strong magnetic field. And then what happens now, once they're heated up and they're put in a strong magnetic field where north is up here and south is here, now they're all spinning in the same direction, then rapidly cool it. And once you do that and it rapidly cools, now these guys will get locked in place again. So now they're all locked, you heat it up, now they're free, now they can start rotating around and maybe even moving throughout the substances, right? Or floating around throughout the substance, because it's a blob of metal. And then what you do is you, once it's heated up, then you put it in the magnetic field. So now they're all rotating in the same direction, counterclockwise, pointed up. And then you rapidly cool it, and now they're locked in place, spinning in the same direction. And so that's how you take a ferromagnetic material like iron and then turn it into a permanent magnetic material of iron. Okay? So there are these levels where you have complete chaos, is unmagnetized, right? So this is a ferromagnetic piece of iron. It's unmagnetized at the moment. And then if you put it in a magnetic field, it becomes a little bit more magnetic. And then you put it in a strong magnetic field, it becomes strongly magnetized, right? And so here's the interesting thing about this, since it's based on density, right? So let's say the area of this, whole thing, I'll remove that line, is 1, 2, so 1, 2, 3, 4, 5, 2, 3, 4, that is 5. So 5, 10, 15, 20, 25, 30. So let's give it an area, right? So it's 30 dipoles per this area, right? And I'm going to just be doing that'll be a surface density. So this is the density. What I'm doing is doing number of dipoles per area, right? It would be per volume, but same thing. And so what's really neat is if you cut it in half. If I cut it in half, and so now I have this guy, which is now 15 dipoles per half area, and this guy is 15 dipoles per half area. Well, now that works out mathematically to be 15 dipoles per 30 dipoles per area, right? So each of these works out to be 30, right? 15 divided by a half is 30, and that's dipoles per area, right? Right? And this is dipoles per area. Well, what does that mean? Well, since magnetism is based off of the density of dipoles in a magnetic material, when you break a magnet in half, it breaks up into two magnets, both with north and south poles, right? You broke it right here. These guys this is the south end of this side, and it's the north end of the other side. And so that transfers down to here. So that north is that north, and this south is this south, right? So, but what happens is when you break it breaks up into two equally strong magnets, right? That have the same density as they had before. So it's kind of really cool how this works out. So since all dipoles have to have two poles, because that's the very definition of dipoles, when you break up a magnet in half, it becomes two equally strong magnets that actually have the same density as they had before, right? So pretty neat. So if, again, we had talked about your refrigerator door, and if you notice, like when you bring a magnet, if you ever brought a magnet close to a piece of wood and you try to see if it sticks to wood, it'll just fall on the ground, right? Because wood has no unpaired electrons, right? But if you take that same magnet and bring it to your refrigerator, it'll stick to it, right? So your refrigerator, you didn't heat up and cool down, kind of like you did in this other slide where you heated it up and cooled it down to make it a magnet. It didn't happen like that. It's just at that moment, when you bring a magnet close to a substance that it can become magnetic, like ferromagnetic material like iron, at that moment, it does become a magnet. So what is going on to make something that is not currently a magnet suddenly become magnetic when you bring another magnet close to it, right? So at that moment, when you bring your that magnet close to a refrigerator and your refrigerator door at that area becomes magnetic. Okay, so what is happening? Well, if you look, your refrigerator door is ferromagnetic material, and at the moment, with no magnetic fields around, is not magnetic, right? But then when you bring a magnet close to this, so when you bring a permanent magnet close to your refrigerator that is ferromagnetic, what happens? Well, if you'll notice here, you have, so these guys are kind of all over the place, right? So you have there are 1, 2, 3 guys. So when you bring a north close to this, a north end of a magnet close to this, right here, just like this piece, notice that there's 1, 2, 3 that would be connecting to it, right? So you have a north and a south, and what you learned from when you broke up a magnet, it broke up into 2 small magnets, north-south and then north-south. So these 2 guys are going to attract to each other. Well, notice that these 3 circled guys are already aligned in the direction that this magnet is facing. So what's going to happen is these dipoles are going to actually grow and become stronger, right? Okay. But notice this guy, and this guy are not aligned in that same direction. Well, this is going to actually grow. This whole piece is going to grow, and it's going to squeeze down this guy and make it smaller. And even though it doesn't show it, this piece right here is actually going to be squeezing this guy down. And it would actually be squeezing, so this piece is actually growing and it's squeezing this piece down and squeezing this piece down. And so what happens is all the guys that are aligned in the opposite direction kind of get squeezed down in favor of all the electrons that are already going in that direction, right? So another way of thinking to it in an overly reductive term is that when you bring a magnet close to an unmagnetized piece of iron, is that it starts to actually make this guy become a little bit more, make an unmagnetized piece of iron, and it induces the poles and tries to get them to actually point in the same direction, right? So the ones that are already pointed in that direction, so they'll be all over the place, and those areas will get squeezed down and become smaller, right? So this guy right here is going to elongate and squeeze down all these other guys, right? So it starts to actually kind of become where the dipoles get induced in the same direction, right? So it's kind of an interesting situation. So the cool thing about it is this: if you have a refrigerator, so if you have a refrigerator right here, and you bring a north side of a magnet close to that refrigerator door, what's going to happen is it's going to induce, and that's what it means by elongating those dipoles. It's going to induce dipoles pointed in the same direction that the magnet is pointed, right? If you brought the south end of a magnet close to that refrigerator door, and I wrote that incorrectly, south end of a magnet close to that refrigerator door, it would squeeze down all of the left pointing norths in favor of the right pointed norths to make those dipoles get emphasized over these other ones, right? So the north would be, so basically it would align in the same direction as a magnet. So that's how you take So that's what would happen to create how you take a magnet and bring it close to a refrigerator door and temporarily becomes a magnet at that point that they're in contact with each other or near each other. So there's all these experiences which we've kind of gone through and that you've accumulated over life. And now we're going to actually start relating them to what a magnetic field is, right? And I mentioned earlier that a compass is essentially just a magnet floating or balanced on a balance beam or in water, right? So the north end of the magnet is pointed north, the south end of the magnet is pointed south. And so that's kind of what this is. By the way, in any quizzes or that you take, or the slides from here, the colored part, brown is typically the color, is the north part of the magnet. Okay? So you know that when you bring two norths close to each other, they repel, and you bring two souths close to each other, repel. That means like poles repel, unlike poles will attract. A north and a south will attract. Well, since a compass is the same thing as a magnet, the north end of the compass is going to be repelled from the north end of this magnet. The south end of the compass is going to be attracted to the north end of the magnet. Okay? And you could use magnets, you know, and these pictures are to illustrate what we talked about before, that you cut a magnet in half, it becomes two equally strong magnets, and that ferromagnetic materials will become magnetic, emphasizing their domains that are already pointed in those directions, right? So anyways, the whole point of this is to show that a compass is basically a magnet, right? And the best way to plot a magnetic field, so I'm going to introduce the idea of magnetic fields, the concept of magnetic fields. So the best way to plot a magnetic field is to actually place a magnet around another magnet, and one that's probably balanced so it could be free to roam, and it'll detect the north and the south of the other magnet. And that way you could actually plot the magnetic fields around another magnet. So these are iron filings, but the iron filings are really cool. So you place a magnet, you spread out iron filings on a piece of paper so it's nice and homogeneous, looks like pepper. And then what you do is you put a magnet in that vicinity under the piece of paper, right? So what will happen is those iron filings will align along the directions of the magnetic field. And further, if you need to, and let's say you didn't know this was south and you didn't know this was north, right? You didn't know what those were and this was not colored. How would you know which is north from south? Well, you bring in a compass, right? And if you place a compass right here, the compass needle, since if the compass needle is pointed up and away from this, that means the north is away, the south end is close to this, which is the north end. Well, if it was pointing this way, then you know that this has to be the north end. And that means this compass needle is going to be pointed down and to the right. The compass needle, weirdly enough, over here would be pointed to the left, right? Notice that the magnetic field lines are kind of going, it looks like they're kind of going out of the north and into the south, right? So right here at this area, a compass needle is just going to be pointing to the left. And if you put a compass right here, it should be pointing right towards the south end of the magnet. Okay? Pretty cool. So now you know that you could use a compass to detect magnetic fields and plot magnetic fields, which is what the lab that we're going to be doing in this section is all about, right? How do you plot magnetic fields? Well, like I said, the compass needle will point away from the north, and then it will be pointing towards the south. So, and that compass needle is free to rotate. And so when you get far enough away from this magnet, well, it's a weak field, so the needle doesn't really rapidly spin to correct itself. It'll kind of weakly and slowly spin. So the strength of the magnetic field is proportional to the torque being applied to that rotating compass needle, right? And if it rapidly corrects itself, well, you know you're in a strong magnetic field. If it's a weak magnetic field, it'll kind of lazily rotate until it finally finds the area. So it's the kind of amount of time that it takes to correct itself, which is proportional to the strength of that magnetic field, right? From that earlier example, what we were using with that magnet and the iron filings, you now know that a compass will align itself in the direction of the magnetic field. Okay, so here we have a magnetic field with blue. They're the blue little arrows that are pointed upwards, right? And you notice, and you'll note that this compass needle will start to align itself in the direction of the magnetic field. Now, in physics, we represent the magnetic field with a capital B, and it's Biot-Savart law, right? So that's why it's a capital B. It's named after the Biot-Savart law, okay? So they're going to align themselves in the direction of the magnetic field, right? This compass will. And the magnetic field is represented by a capital B, and we're going to be using arrows to represent that magnetic field. And again, the arrow point, the north end of the arrow is north, the south is the other end that has no arrow attached to it. So that means this entire magnetic field, north is up top here, south is on the bottom here. And so what you would find is that this guy will align itself in the direction of that magnetic field. Okay? So eventually this compass needle will be pointing straight up in the direction of the magnetic field. Okay? And so back to our little bar magnet, when you place a bunch of compasses, compassi? I'm not sure what the plural of compass is. In the direction of this, all around this magnet, what you find out is that you're actually really, again, like those iron filings, you're plotting the magnetic fields at each one of those points. And the magnetic field will be pointed away from north and towards the south. And so you get this really cool these lines that are going, and they look like they're emanating from the north and going into the south. And then this guy is going straight out. This guy is coming out and going around, following these guys and coming in. So all of these magnetic fields are coming out and going into they're emitting from the north end of the magnet and towards the south end of the magnet. And notice that the compass is pointed in the direction of those magnetic field lines. The blue is the magnetic field lines, and the compass, again, the shaded area is the north end of the compass. White is the south end of the compass. So the compass will point in the direction of the magnetic field. What are you supposed to do with that? Well, what you're supposed to do is you're supposed to smooth over those drawings. See, if you look at this, it looks pretty terrible and not too presentable, right? But what you do is once you draw more and more of these lines and you get those compasses really close together, well, now it starts to take on a smooth shape, right? And you can see all these lines are leaving the north end and then wrapping way out of the picture actually and coming back into the south end. This guy is just leaving straight north, right? But eventually these guys that are off axis are going to come way back around and come back into here. So this guy is actually connected to this guy. This central axis line is, those ones are the only ones that actually don't come back in upon themselves. Okay, so it's kind of cool. Basically, this is how magnetic fields are represented, right? And again, that's a capital B, and it's a vector too. So if you had a magnet right here, and we just saw this picture, well, you zoom out and it starts to become this, right? So you can see how those magnetic fields are wrapping in upon themselves. Well, what do the magnetic fields look like when you have two magnets close to each other, right? Well, what it looks like is that the magnetic field right here is pointed to the right. Well, if you bring north close to north, those magnetic fields are going to be bending away from each other, right? So right here in the center, right here, there is actually no magnetic field. The B field at this point is 0. So if you put a compass right here, it would be free to move. It's actually pointed in no direction. It's pointed in all directions and no directions at the same time. It doesn't know what to do. And it doesn't rotate in place like in the movies. If you stand on the South Pole, how they show in the movies, and that's just a compass would be rotating. That doesn't happen. If that happened, then we'd have a permanent power source to power the Earth, right? That's not realistic. What happens is you put a compass needle right here at the center where there is no magnetic field, and the compass will point just wherever you happen to be pointing it. Okay, it'll point wherever you place it. Okay, it won't point in the direction of a magnetic field at all. So what happens is magnetic fields kind of bend away from each other. They're trying to go from north to south, but when you bring two norths close together, well, they're going to bend and try to wrap in upon themselves since they can't just go straight across. This is what happens. So that's what repulsion looks like, by the way, when the magnetic fields are bending away from each other, right? So at that point, there's actually where there is no magnetic field, there's actually a repelling force between these two, right, on each other. Here, notice that you have a north end of a magnet close to a south end of a magnet. Now the magnetic field lines will go straight towards them. So now you actually have a very strong magnetic field. So magnetic field is going to be strong at the center and pointed to the right. In this case, towards south. Right is south. In this case. So all these magnetic field lines from the north end are now trying to attach to the south end of this magnet. Meanwhile, the magnetic field lines down here are closer to its own south end, so they're just going to wrap right around their own, right? Whichever one they're closer to, they're going to favor, right? So this is kind of a net effect. It actually does send field lines over to here, but it kind of gets de-emphasized due to these guys, right? So this is kind of showing the net effect of the magnetic fields, but overall, this is what attraction looks like, is when the magnetic field lines are directly connecting, while these guys are not connecting, they're repelling from each other, right? So this is attraction, this is repulsion. This is two spiders hugging, this is two spiders pushing away from each other. Anywho, moving on. So now that we know that if you bring a north end of a magnet, it should be trying to connect to the south end of another magnet, right? And we also talked about if you had a so I'm going to reverse this. You have a north end of a magnet here, south end here, and you had a compass needle. You had a compass right here. Which way should that compass be pointed? It'll up, down, left, or right. So it should be pointed down, right? Well, if you think about it, that's kind of weird, right? If a compass needle here, in this case, is pointed away from the north end of a magnet, right? But we use compasses on the Earth for us to find north. So isn't that a little confusing? How come a compass needle is actually pointed away from north, away from the north end of a magnet? But we use a compass to find the north pole of the Earth. Well, how is that possible, right? Is the Earth a different kind of magnet, or is it the same kind of magnet, right? Well, what we found out was that it is actually true. A compass needle does point towards the south end of a magnet, which means this: while the top of the Earth is what we call geographic North Pole, GNP for short, the actual south pole of the Earth, the actual south magnetic pole, is actually where we think the North Pole is. Okay? And right now it's actually kind of floating around for the last couple 100 years. It's been kind of floating all over different parts of the Earth, but it's mostly in this region, the top of the Earth, right? By 23 degrees. The point that I'm saying is this, is the top of the Earth is the South Magnetic Pole, SMP. But that's what we call geographic north. Okay? So this whole time that you've been holding a compass and walking north, you're walking geographic north, but that's actually polar magnetic pole south, or south magnetic pole. Okay? And the bottom of the Earth, or the southern part of the equator, that is actually magnetic North Pole, but it is geographic South Pole. Kind of cool. So hopefully that kind of blew your mind a little bit. So what you find is that geographic North Pole is up top here. That this is also the in the vicinity of the magnetic South Pole, right? Magnetic South Pole, right? And the Earth creates its own magnetic fields. Again, just like a regular magnet, its magnetic fields leave the north end of the South Magnetic Pole. So the North Magnetic Pole, South geographic South Pole, I should say. So the North Magnetic Pole is on the bottom of the Earth, and here we are in Arizona, right here, and our magnetic field, our compass, should be pointed up and to the right. Right? So it is. So that's the north end of our little compass, and this is the south end of our compass needle. And that means it's pointed towards the South Magnetic Pole on top of the Earth. And so that's the reason why when we're walking around in Arizona, our compass needle is pointing towards up and to the right. And it's just pointed along the magnetic field lines. So how is the Earth itself a magnet, right? Well, what we learned before, that for something to be a magnet, it has to have those unpaired, quantized electrons, right? And so the idea is this: since the Earth is a big blob of fluid, right, and heavy stuff will sink and light stuff will float. All the heaviest metals have over time sunk down to the center of the earth, right? And the heaviest of metals is actually is iron. Iron is super heavy, right? So at the center of the earth is iron, Fe, or iron, right? And all these other types of heavy metals. So at the center of the earth are is a ferromagnetic material. And so the earth is rotating and spinning on end. Well, that's causing the center of the earth to spin, which is causing all those little electrons to spin in the same direction, right? Those unpaired electrons, if everything's rotating around them in the same direction, well, that causes friction and rubbing and kinetic energy of all those atoms. Well, that's going to then carry on to the unpaired electrons, right? And so what happens is everything seems to be rotating counterclockwise, right? So the Earth is rotating counterclockwise. And so now you have a bunch of moving electrons rotating all around, moving all around, and they're all rotating in the same direction, right? And so what is a moving electron if it's moving due to friction, and if they're all moving in the same direction? Well, what you find out is if they're all moving to the right, let's say you're standing on the equator, so you have electrons, the direction, the velocity of the electrons is moving to the right, well, you'll have a current pointed to the left, right? Remember, moving electrons are what causes a current. So at the center of the Earth, all these moving electrons, which are moving around in a circle, are moving to the right. Well, that means they're creating a current pointed to the left. And that is what is responsible for the magnetic fields, right? So these moving electrons at the center of the Earth, these unpaired moving electron, little dipoles, are moving to the right. And that is creating basically a current to the left. Okay? And so, by the way, that arrow's motion of the Earth. Right? So at that moment on the equator. So that shows you what's happening in the center of the Earth. So this has some really cool consequences, right? So if you have a magnetic field, again, the magnetic field, the Earth is a huge magnet, and it's pointed down and up. Well, there are all these charged particles in the universe that are coming in, most of it coming in from the sun, but there's also cosmic rays in general from outside our solar system and also inside our solar system, not from our sun, that are hitting the Earth, right? And so what happens is the Earth's magnetic field makes up these kind of belts. They're called the Van Allen radiation belts, right? So these charged particles get trapped in the outer reaches of the Earth's magnetic field, right? So here's the Earth's magnetic field, right? And so you get all these charged particles now that get kind of trapped, and they start to have to be almost kind of orbiting just like that, right? So orbiting the Earth just like a satellite, sort of, due to the Earth's magnetic field. Well, that has some really cool things. So what happens is you get these charged particles that are getting deflected north and south, just like a capacitor, right? And we'll talk about how charged particles get deflected due to a magnetic field later on. I think that's 5.4 or something like that. Anyways, they create these really cool aurora borealis effects, right? And so the sun, which will have these storms, will will release a bunch of charged particles, and some of that charged particles will get trapped on the outer reaches, but some of them will break through and get and then create these corkscrew effects. And so when they hit the Earth's atmosphere, those charged particles will have to slow down, right? And when they slow down, they start to release energy in the form of photons. Electrons, when they slow down, release energy in the form of photons, and the amount of energy gets released, meaning the amount of energy that gets released from them hitting the Earth's atmosphere will release different colors, right? So different colors will have be associated with different types of energies. Okay, so that's how you get. That's why you get these weird effects due to the Earth's magnetic field. So what I want you to do from here is I want you to go ahead and go on to your sapling homework, and well, actually, I want you to first do the lab, and then do the lab, and then start working on your homework assignments. Okay, and do the readings. Thank you very much.